So hello everyone, let us solve today's GfG problem of the day, and the problem name is 01 Knapsack Problem. So let us read the problem statement. So you are given weights and values of items, and you need to put these items in a knapsack of capacity capital W to get the maximum total value in the knapsack. Now they have given the note that we have only one quantity of each items. So in other words, the question is saying that you are given two arrays, val and wt, which represents values and weights associated with items respectively. Also given an integer w which represents the knapsack capacity. We need to find out the maximum sum of values subset of val such that the sum of weights of this corresponding subset is smaller than or equal to w. Now you cannot break an item, that is either you can pick the item completely or you don't pick that item. That's why the problem name is 01 knapsack. 0 means nothing, 1 means completely. So let us see one example and try to understand the question and find some solution out of it. So this is the example which I have taken. So this is the value array, this is the weight array, and this is the weight or the capacity of the knapsack which we have. So what the question is saying that we need to pick these items from the values array and its corresponding weight is given in the weight array. So we need to pick these items, and what we have, just we have some knapsack, let's say. So we have this knapsack, so we need to put items in this. Now the knapsack has some capacity W, or weight, or the maximum weight which it can hold is W. Now we need to choose these items in such a way that the weights of these items which we have been provided here should not exceed this W, as well as we need to maximize the values which we have taken. So whatever value we are getting, let's say this item has some value x, this item has some value y, this item has some value z. So we need to maximize the value of x plus y plus z in another condition which they have provided, that the weight of these items x, y and z, the summation of weight of these items should be less than or equal to this capital W. So this is what the question is saying, and let us find some solution for this. So we need to find the maximum thing here. So whenever we have the term like maximum or minimum, what we do first, we try to solve the problem in greedy way. But if you apply this greedy solution here in this question, it will fail. Now why it will fail? So greedy is applicable, like where will you apply greedy? You need to maximize the summation of these values. So if you apply it on the basis of value, there is another constraint that we need to take care of these weights also. So here we need to consider two things, so it becomes difficult to apply greedy. Now this is not the only case why we are not applying greedy. There is one more scenario. I have taken this example for that scenario only. So let me give you one scenario. So let us say we put like according to greedy, among these three value, what value you will choose first? Obviously 100 is the maximum, so according to greedy solution you will pick the 100 value first. Now if you put the 100 value first in your knapsack, your weight of the the capacity of the knapsack will become 0, because you have taken the weight of 4 by choosing this item of value 100. So now you have the item of value 100 and now your knapsack is full. You can't fill any more items in your knapsack because the weight now becomes 0. So according to the greedy solution, the maximum value which we got here is 100. But is it really the maximum possible? No, it is not. Let me tell you, there can be more maximum value according to some other scenario as well. So instead of taking 100, let's say we choose 99. So if we choose 99, the weight, so let me rewrite this. So weight is initially 4. Now we have chosen this 99. So if we are choosing this 99, its weight will also be deducted from the capacity. So now our new weight will be 3. So if our new weight will be 3, that means we can choose another element which has the weight less than or equal to 3. So yes, there is one element whose weight is less than equal to 3. So we can choose this 99 as well. So we choose two 99 values. And now we need to subtract this one from our capacity. So we subtracted and the new capacity is 2. Since there is no item left whose weight is less than or equal to 2, we have these two items in our knapsack and the summation of these is 198. Now this is the maximum possible value which we can get. Now we didn't apply a greedy way. Greedy failed here. So how did we get this solution? So this is a kind of scenario where you need to find the maximum possible answer and your greedy solution is failing. So whenever your greedy approach is failing, you can think to explore all the possibilities. All the possibility means, now if you are standing at some particular item, you have two choices. Either you can take that element or you can not take that element. So these are the two choices which we have in each and every scenario. So we will try out both the possible case by taking that element and not taking that element, and whatever result we are getting from these two, we will take maximum of those, maximum of take and maximum of not take. So whatever maximum value of we are getting from these two scenario, we will take that only, and by this we can find out the maximum possible answer. So this is the approach which we will use. Now if we try to check each and every scenario, like take and not take, so what will be the time complexity here? So we have two scenarios, and for each and every element we are having two scenarios. So if there is one element, we have two scenarios. If we have two elements, let's say 1 1, so here we have two scenarios, here we have two scenarios. So it will not occur in this way, it will be in some recursive tree. I am just drawing it this way. So if we have two scenarios, we will have four we need to check 4 possibilities. So what we can say that if we have n items, we will have 2 to the power n possibilities. Now according to the given constraints, our n value can be as max as 1000. Now if this is the n value, then 2 to the power of 1000 will give us the time limit exceeded error. So recursion is not possible. So what can we do? So we can optimize with the help of dynamic programming. So we will convert this recursive solution into DP with the help of memoization. So let us see how will we apply the DP solution. So whenever we are having a question of DP, we have two things to consider. One is the size of the DP, or you can say, let's say, the states of the DP, and the other thing is the transition of the DP. Now transition we have already seen. Transition is take and not take. So in take condition, what will be the transition? We will simply take the value of I and we will further call the recursion function and we will get the answer for that. In not take, we don't have to take any value. So 0 plus we will call for the further recursion, and we can just call this function for the next elements. So this will be the transition of our DP. Now what will be the states of DP? So states of DP depends upon number of changing parameters. So number of changing parameters decide the states of the DP. So in this case, what are the changing parameters? So obviously if we have some value array, let's say some values are given, so we need to check each and every possibility for each and every element. So let's say we are iterating with the help of I. So for this x we will check two possibilities, for this y we will check two possibilities. So we are going on to each and every element. So one changing parameter is the index only. So one changing parameter is the index, let's say I. And what is the other changing parameter? So what thing is changing continuously? So if we are taking the value, if we are taking a particular item, our capacity of the knapsack will be reduced by the weight of the current item. So you can see that if we take a particular item, our knapsack capacity will be reduced. So other changing parameter will be the knapsack capacity. So we will have these two changing parameters. So if we have two changing parameters, we will have 2D dp. So transition is clear, state is clear. So we will have 2D dp, and size of the dp is simple. You can just write like this. Since n value is 1000, you can, for safe case, you can write it as 1002, and the weight value can be, or the capacity, maximum capacity given is also 1000. So to be on the safer side, you can write like this. So this will be the size and state of our dp, and this is the transition of the dp. So we have discussed how we will approach the dp solution. So let us write the code now and understand in more better way. So let us see the code now. So first of all, we will declare our 2D dp globally. So what will be the size? It will be 1002 and 1002. So why we have taken this size, we have already discussed. So let us first initialize our dp with all values as -1. So it will be helpful for our memoization condition. So memset dp -1 size of dp. So this will set all the values in our dp to -1. And now we need to write a memoization solution. So we will write recursion for that, and then we'll memorize it. So we will write the recursion in this solve function. So this solve function will give us the final answer. So in this solve function, what all parameters we will have? We will have this weight vector, we will have this value vector, we will have the capacity of the knapsack, and we will have the index by which we are iterating. So initially our index will be pointing to 0th element, so we'll start with 0. So let us write this solve function now. So it will return us the integer value, the maximum possible summation of all the values which we can get. So it will be integer, so it will return us the integer value. Solve, and let us write these parameters now. So vector of int weight, vector of int and weight, vector of int and value, int w and int. We are iterating with the help of I pointer, so I have declared it as I. So in the recursion, first we have the base case. So what will be the base case? The base case will be if we are at the last element. Now if we are at the last element, that means our I is equal to weight dot size -1. So if we are at the last element, we will have two choice. Either we can pick that element or not pick that element. So what is the condition for picking that element? So if that ith element has weight less than equal to the total the current capacity of the knapsack, then obviously we can pick that element into our knapsack and store it in our knapsack. So for that we will pick that element, and if we pick that element, what will be return its value? It will we will return the value as value of I, because this is its corresponding value for that item. Otherwise, if our knapsack doesn't have this capacity to hold this item, so we don't have to do anything. So we'll just return 0 because no value will be added to our answer. So adding 0 is perfect. So we'll return 0. Now what we have seen, we will have two scenarios, either take or not take. So if we are taking a particular element, we will we need to check one condition, if our knapsack has the capacity or not. So same here. So what we will do, if weight of I is less than equal to the current knapsack capacity, then we can add it into our answer, or we can just put that item into our knapsack. So in that take condition, what will we do? We will take that value of I and call this function again to solve the further cases. So what we will do? The weight vector will remain same, the value vector will remain same. Now W will change. Now if we are putting that item into our knapsack, the knapsack capacity will be reduced by the weight of that item. So we will subtract that. And since we need to move further to the next element, we will just increment our I by +1. Now in the not take condition, we are not taking anything, so we will simply move on to the next index. So weight will remain as it is, value will be same, weight will be same because we are not adding anything. So simply moving on to the next item. And in the end, what we need to do, we need to take maximum possible answer that we are getting from this take and not take. So not take. Yes. So this was the recursion. Now we need to memorize this. So for the memorization, we will have the condition if dp of I comma w is not equal to -1. That means we have already solved this sub problem before. So we don't need to solve this again. So simply return that dp of I comma w. Now in the end, after solving this case, we need to store the maximum answer. So we can store this particular case into our dp. So we can just write like this: whatever answer we are getting, maximum of take comma not take, we will just store it into our dp so that we can apply this memorization condition if this condition occurs again in the future. So this was it about the dp solution. So let us see if this code works fine or not. So let us submit this. So yeah, it is passing all the test cases. So our solution got accepted. So hope you learned from this video. Thank you.